Okay, well, hopefully everybody did a great job working with our permutations here, whether you're using the box method or using the calculator, either way. So for our combinations, so what we're going to do is kind of start off with an example to help us motivate what's going on here. So suppose we're working at a pizza parlor and we have a special on three topping pizzas. How many different three topping pizzas can we make if we have the following toppings and you can't reuse any of the toppings? So we've got ham, sausage, pepperoni, and mushroom. So we've got four different toppings and we're allowed to choose three of them on our pizza. So what we're going to do is we're kind of going to brute force this out and actually just write out every single possibility to see what we get. And so I'm going to start off with, say, ham, sausage, pepperoni. And so what if I were to write this down? Is that a different pizza than the one above, or is it the same? So hopefully you're saying it's exactly the same, because with a pizza, does it really matter whether you put the ham on first, then the sausage, or the pepperoni first, then the sausage, or the ham? So for this one, we can kind of put the toppings on in any order that we want, and it doesn't really matter. So the order of these doesn't technically matter. We're more focused on just making sure that the toppings are actually on there. So if we look, so ham, sausage, pepperoni would be the same as sausage, ham, pepperoni, pepperoni, sausage, ham. So I don't have to list each and every one of those. All right, so with that in mind, I'm going to go ahead and leave ham here. And I'm going to swap out pepperoni for mushroom. And then I'm going to swap out the sausage, pepperoni, and mushroom. And then I think that's ham paired up with everything. Good. And so finally all we have left is sausage, pepperoni, and mushrooms. So it appears that we've got four possible pizzas that we can make using these three or four toppings, choosing three of them at a time. So again, this is a nice brute force way to do it. Not ideal if we're dealing with 50 things, for example. We definitely wouldn't want to brute force something out with 50. So with this combination that we're doing, we definitely are going to want to have some kind of a formula or something like that. Or luckily we've got our calculator in order to help us with this. So for a combination, so again, the big thing to notice difference-wise, so it's similar to a fundamental or to permutation in the sense that we're choosing things from a similar group, but they can't. The order doesn't matter. That's going to be the big difference between these guys. So we can't reuse items, just like we couldn't reuse items for permutations. But the order doesn't matter. That's going to be the big difference between whether we're using a permutation or a combination. So permutation, order matters. That's what allows us to write those boxes and list the numbers. Combination, since there's no order, we can't write down boxes. We're going to need some special way to actually calculate what that number is. All right, so if we look, I do have the formula down here for a combination. Again, I don't necessarily want you to use the formula, but I do want to make a note of sort of the difference between the permutation formula and the combination formula. So our permutation formula looked like this. So it's almost exactly the same, except for one piece. This should be n factorial. So the permutation formula is the same as the combination formula other than this one little piece. So notice on the combination what we're doing is we're dividing by r factorial. And so the reason we're dividing by r factorial is because a combination is not going to double count things. Like remember above when I said like ham, sausage, pepperoni was the same as sausage, ham, pepperoni. If we were thinking of that as a permutation, those would get counted as two separate items in our permutation group. And so we don't want to double count those in a combination. So this dividing by r factorial is dividing out all the duplicates. that we get from a permutation. So what that means is our permutations are going to be really, really, really big. Our combinations are going to be, they still could be big, but they're going to be smaller. So combinations are always going to be smaller than permutations. So our combinations are going to be smaller than a similar permutation. All right, and so using the above as an example, I'm going to show you how you use the calculator, and then I'm going to compare the difference between doing a permutation with this set and a combination. So with this one, since we had 4 possible choices of toppings, and what we did is we chose 3, so our R is going to be 3 for this. So in our calculator, what we're going to want to do is use this 4C3 version. And so if I go back to our calculator, go to math, go to prob. So notice number 3 is our combination NCR. And so I want to hit 4 for the first, 3 for the second. And so lo and behold, we got the same answer as we did before, which was 4, which was nice. And so again, not that this was a permutation, but let's just see the difference in size. So imagine the topping orders did matter. And so we wanted to treat this as a permutation type problem. So if we wanted to treat this as a permutation problem, if we did 4P3, notice in this case we ended up with 24 possible pizza choices. So again, we know like that's not legitimately true because again, doesn't matter what order you throw the toppings on there, but you can see what a significant difference there is between a combination and a permutation. Those numbers can be drastically different. And again, the reason being is because the permutation is counting all these kind of duplicates that the combination is counting as one single item. All right, perfect. Very good, everybody. So again, let's take a look at trying to figure out when is something a permutation and when is something a combination. Because again, that's going to be one of the harder things to try to decipher. So it's not too bad if we know, hey, this is fundamental counting, this is permutation, this is combination, but trying to identify which one is which can be a little trickier. So let's look at example 7 real quick. So for this one, we're just trying to identify which is which, whether it's a permutation or combination. So how many ways can we select 6 free videos from a list of 100 videos? So again, the thing you're going to want to ask yourself is, does order matter? So if I'm looking at this thing, does it matter what order I choose these 6 videos in? And so I would say no, because I mean, if they're just in a big bin or something like that, you're just pulling them out. You could rearrange them in your hand. You could do all kinds of stuff with them. So in this case, order doesn't matter. And so because of that, that's going to be our combination. And so I'm not going to solve it out, but if we were to write it in formula form, this would look like 100C6. So I'm not going to type in the calculator or anything like that, but just if you wanted to see it. And so with B, we've got a race where there were 50 runners, no ties, and how many ways can the first 3 finishers come in? So with this one, they're trying to put a ranking on people. They want a first place, a second place, and a third place. So the fact that they're putting a ranking on it means that order does matter. So order does matter. So what that means is I could draw a box for first place, a box for second place, and a box for third place, since I'm trying to find the first 3 finishers. And so what I'd have is I'd have 50 choices for who could come in first, 49 choices for who could come in second, and then 48 choices for who could come in third. Or if we were thinking about this using our little P formula, this would be 50P3. All right, perfect. So again, always ask yourself that question about combinations and permutations. Does order matter? Does order matter? Does order matter? That's going to be the most important part to try to decide whether we're choosing a permutation or a combination. All right, so for the next 4, 10, 11, 12, and 13, all of these are combination problems, so you don't have to decide which one is which. So try those on your own. And then for the next 5, so 14, 15, 16, 17, and 18, these could be any. So these could be permutations, combinations, or fundamental counting principles. So you want to kind of try to pick and choose which ones you think are correct. If you need help on them or hints on them or anything like that, just let me know. If you want to see any of them written out, just send me a message. Now, I will give you a little bit of a hint. Whenever we're dealing with card games, for example, if you play cards, usually what happens, someone deals you a deck of cards, the first thing you do is pick them up, and depending on what the game is, you reorder the cards in some way. And so by moving them around, they're not a different set of cards or anything like that. They're still the same hand that you had before. So cards are always going to be a combination unless they happen to say order matters. So for us in this class, card games are always going to be combinations unless it specifies order matters. So kind of keep that in mind. All right, so good luck working on these. Let me know if you get stuck or have any questions. This is an important section because if you can get this down, it's going to make the next section much, much easier, because in the next section we're going to be dealing with probabilities of these different things. So we're going to end up with like combinations on the top and the bottom, permutations on the top and the bottom, stuff like that. So good luck, ask questions if you have any, and otherwise I'll see you in the next section.